Hello, students. Got some 8.2 questions, so thank you so much for sending those in by email, 824-6789-12 and 13. Let's take a look and see if we can get a nudge in the right direction. And let's see here, so 4. Okay, so come down here. Oops, I got to go back to the previous. I guess it's right here. So here's 4. Okay, building a matchstick. Used 599 to form the last 2 figures in the sequence. How many matchsticks did he use in each of the last 2 figures? Okay, so your goal is to find how much did he use in each of the last 2 figures. Okay, so let's see if we can maybe make a pattern. There's a couple ways to approach this, but try to find, some kind of a connection, right? So option 1 is to, yeah, I can think of at least a couple ways to maybe approach this. You could look at this and say, let me find a pattern for the entire sequence, and then generalize to any 2 terms in the sequence, add those together, set that equal to 599, and go from there. The other way is to maybe try to shortcut it by just seeing if I can make a pattern of the sum of the 2. So if I add these 2 together, how many total are there? So I'll probably, maybe I'll start with that one, at least nudge that way and just kind of say, hey, how would this work? But let's take a look and see what that would look like. Here we go. All right, so if I was to add these 2 together, right, I've got 4 here, 4, 5, 6, 7 plus 7, that gives me 11, okay? Then the next, so off here, I'd put 11, that'd be my first 2 terms, right? Next up would be 4, 5, 6, 7, so 7 plus 7, 8, 9, 10 plus 10. So that'd be 17. Okay, so my next one is 17, right? So I'm making a sequence of 2 together. See what I'm saying? So I'm trying to, instead of thinking of this just as a single sequence, I'm just trying to do kind of what it says because it says the last 2 figures. Okay, next one would be 10 here, and 10, 11, 12, 13, and 13. So 10 and 13 be 23. Okay, 23. Okay, so what's happening then? So as I look at, this is the first 2 figures added together. This is the second and the third figure added together. This is the third and the fourth figure added together. And I'm noticing a bit of a trend, right? I can see I'm adding 6, and then I'm adding 6, dot, 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 dot. Now, at some point in time out here, I have to get to 599. Okay, so now I could figure out, how far down the road that is, and then see kind of how many are in each one. And what helps me here is noticing a little bit of a pattern. See, the first one and the second one are very closely related. They're just off by 3. So if somebody told me 17 was your magical number instead of 599, if they said 17, I could say, oh, okay, then it's I don't know how much plus I don't know how much plus 3. And if I pull that 3 off of there, I get 14 equals question mark plus question mark. And that means, because there are 2 question marks, I got to be 7 in each. And that is exactly what I would have here. I'd have 7, and the one after it would be 10. So I could find those 2 separately. Okay, so we've got an idea, we've got a plan. Now all I need to do is build the sequence. And remember, the arithmetic sequence starts with that first term and it adds n minus 1 common differences. Our common difference was 6, and we know we're supposed to have 599 at the end, right? And so we can see how many terms that is, I guess, if we wanted to. But I'm gonna, you know what? I'm gonna wait on that. Let me just see here. Okay, because what I want to do is, if it is 599, actually, I may not even need this. Look at my happy face. I may not even need that formula, because knowing that 599 is this type of a sequence, then I would just do 599 is equal to question mark plus 3. Take 3 away from here. So on both sides, just take away 3. That gets rid of that. And then I have 2 question marks is equal to 596. All right, I got to grab my calculator here. 596, and what would that be? 596 divided by 2. And it says 298. So question mark is 200, oops, 298. And there it is. Now it says, how much did he use in each of the last two figures? Well, I know 298 was one of them. And don't forget, the other one was three more. So I would say 301. And there are the two that I would use. Now you'll notice here, I didn't have to use an arithmetic sequence at the end. I looked for patterns and I tried it. Now this is inductive reasoning, but it oftentimes can get you there pretty quickly. Okay, so anyway, that's the idea. Now let's see here. What if you're like in the middle of a test, you like don't see it? Well, fine, use an arithmetic sequence then. Go right ahead. There's nothing wrong with it. So here I could say this is 4. This one's 7. This is 10. That's 13. So I see a sequence here of toothpicks, and maybe we'll want to call these the n numbers. And then we'll have t of n, which is the number total, right, in any sequence. So we can see this is arithmetic, and my common difference is 3. So I would say, okay, my first term is 4 plus n minus 1 times the common difference of 3. And this becomes 4 plus 3n minus 3, which becomes 3n plus 1. Got it? So this is one term in the sequence. And so what I do is I come up here and I say, okay, that's one term in the sequence. That's the nth term is 3n plus 3. Oh, plus 1. Plus 1. Now think about it. What's the next term after that, right? Well, the next term after that, with a common difference of 3, I just add 3. So what I'd actually say is I'd say, okay, my n plus 1 term is 3n plus 4, because I'd add 3 and bring me up here. Nothing wrong with that, right? So then what I could do is I could say, okay, well, now what I want to do is I want to find n. So I could solve for n. And what that means is I'd have 3n plus 1, that's the nth term, plus the last two figures. So I'd add 3n plus 4, and that has to equal 599 toothpicks. Okay, so 3n and 3n gives me 6n plus 5 equals 399. And then I'll just subtract 5. Where's my red pen? There we go. Take away 5, right? And we'll come right back. That gives me 6n equals 394. Oh, see, that looks a little strange. Let's make sure I got that right. Yeah, every one of them is one more than the multiple of 3, so that makes sense. And then I take these two terms, it's supposed to give me 599. There we go. Yep. This one, okay. And let's see here next up. So 3 divided by 6. Yeah, see, that gives me an n value of 65.6. That doesn't even give me a whole number for my term. But if it was 65 on the term, 65 times 3 plus 1 gives me 196. Those two added together. Oh my gosh. Can you see this? I can see it. You're probably screaming at your screen right now. Come on, Fallstrom. I know what you're saying. I feel it through the screen. How about a typo? Because I was getting so excited about subtracting 5, but over here I had a whole bunch of 3s that I actually wrote 399 instead of 599. Yeah, so yeah, teacher's human. Make that a 599, make this a 594, and now that's why I was freaking out a little bit because I looked at 394. It has to be divisible by 6. I could see it's divisible by 2, but if I add the digits up, it does not, it's not divisible by 3. So in my mind, I'm in the video, I'm like, oh gosh, they're gonna see this happen. Train wreck. Don't look away. All right, here we go. 594 divided by 6. There we go. N is equal to 99. So what does that mean? Right? That means Ryan used the 99th term and the 100th term. So when you go back and you kind of plug in, put in 99, T of 99 is 3 times 99 plus 1. And so you just plug that in. 3 times 99 plus 1 gives you 298. And guess what you do if you do it right down here? It's 3n plus 4. So I actually get 301, which is T of 100. And these are the last two. That's how many matchsticks are in the last two. So I've shown two different ways to do it, right? One is very much like I see an arithmetic sequence, work through an arithmetic sequence. Nothing wrong with that, as long as you don't write the wrong number down. But maybe that's a little bit more. Kind of is a little bit more if you look at it. Nothing wrong with it, but it works just fine. Whichever way works best for you. All right, let's see here. 4, then we said 6. Okay, 2 million to 4 siblings. Let's see here. I think I might have done a couple of these. I'm just jumping into Canvas real quick to see if I did. Because remember, if they are posted, you're welcome to watch them. You don't have to wait and make your own video. You're welcome to watch any of those. Okay, let me log in. Okay. And let's jump into Canvas real quick and see. God does the flashy thing, I swear. Tells your computer's old or it's real slow or something like that. Let me come down here to my video page. 8-2. So number 3 and number 9. So let's see here. Is that what we've got on our list? 3 and 9. 9 is on there, but looks like none of the others. Okay, so that's perfect. That'll work fine. Okay, so here we go. So let's jump back to it. So next up was number 6. 2 million left to 4 siblings. The eldest is going to see 3 more times than the youngest. Okay. Remember, when you're answering these questions, the thing that I want to kind of have in your head is, what am I missing? Like, what do I wish I had? What would make this question easier if I knew it? Because that's the idea of algebra. Algebra is just saying, I don't know something. These are unknown quantities. And so at the elementary school level, you move from the idea that I always know what I'm adding together. I always know what I'm subtracting or multiplying. And now we're going to throw in the fact that, man, maybe I don't know. And how can you still solve it? So let's see here. The eldest is going to receive 3 times as much as the youngest. The other 2 siblings receive 16 more than the youngest. Okay. Okay. So if I was reading this out loud, I would look at this. Okay, I got 4 siblings. I don't know much about them, but let's just say, here we go. 1, 2, 3, and 4. There's my 4 siblings, right? I don't know much about them. What do I know about them? I know there's a youngest. And it looks like the oldest gets 3 times as much as the youngest. And then the middle ones, they receive a certain amount more than the youngest. So if you were just to say, here's the youngest, right? Just ask yourself, how much money do they have? Now, here comes the fun of algebra. You can use variables like X or Y for youngest. You could, though, I mean, you're going to be teaching elementary school, right? So you could say $1 sign. That's how much money they had. It's a symbol. It represents the quantity. Of course, you could, if you've been watching what I do in class, use a cloud. There's my youngest. Here, over here is the eldest or the oldest. Eldest. Yeah, some people living in the past. So eldest over here. Now, they received 3 times as much as the youngest. So if I knew how much the youngest had, the eldest is going to get 3 times that amount. Okay. And what do we know about the youngest? Okay, then we have the middle ones. We got 2 more middle ones, and they each receive 16,000 more than the youngest. Now, the youngest one kind of got screwed, right? They didn't get much, but it means they got 16,000 more. So I would put $sign plus 16,000. Again, I just don't know how much the $sign is. And before long, you can look at all of this and say, let me just add those all up. If you are someone who's like, $sign, my teacher would never let me do that. Okay, fine. Call it X. And then all of these $signs are just X's. You see, it didn't change anything. When you add them all together, count up how many X's do you have, plus how much from the other dollar amounts. Just add up everything that you see right here and set that equal to your 2 million. and then go through and solve for the value of x. Okay. You could also do this one with guess and check. I would not recommend it because it's a whole lot of plugging things in and then adding things up. Algebra saves you here. So try that one. That's my nudge. That's my big push in the right direction. Let's see here. Question 7 comes next. 10 years from now, Alex's age will be 3 times her present age. Okay. I know some of you, when you see these problems, you do a little freak out because you've had some anxiety with them in the past. I wasn't there, right? I didn't cause that. So let's just give these a shot, an actual real shot. Okay. So here's the thing. Look at what it's telling you, right? It's like, find Alex's age now. Here's a big hint. Why don't we call that something? I don't know what it is, but here's Alex's age right now. There we go. And we'll make a little note. A equals Alex's age now. Done. That's her age right now. So if someone asks you, how old is Alex right now? You'd be like, I know. It's A. Okay. Now you might be saying to yourself, but I don't know the number. Chill out. Just breathe for a little bit. It's okay that we don't know it right now. Let's use the other clues and see what we can figure out. Now, the next thing is 10 years from now. Okay, hold on. This is now, right? Here's my timeline. So over here, I got 10 years from now. Well, how old is she going to be 10 years from now? How old are you right now, right? So let's just say that you're 20 years old right now. How old are you going to be 10 years from now, right? You're going to be 30. How'd you get there? And you say, oh, I just added 10. Awesome. How old is Alex right now? And don't say you don't know because we just wrote it down. Alex is A. Perfect. How will we figure out Alex's age 10 years from now? A plus 10. Yeah, that's it. This is Alex's age in 10 years. Done. So now I know how old she was now. I know how old she's going to be 10 years from now. And now I just take that information and I put it into what they tell me, because now they have to create a relationship. They have to create a representation. 10 years from now, Alex's age will be, so will be is like is, that's your equal sign. 10 years from now, her age will be, that's the is or the will be, 3 times her present age. So this thing is equal to 3 times her present age. What is her age right now? Huh. If only that was written down on the screen. Boom. Put it in and then solve. Okay. Push. There's your nudge. Let's see here. I think same type of thing for this one. Number 8 is up. Yeah. So same type of thing, right? Ask yourself, what do I know? What do I not know? And if you can say, hey, I don't know how many stickers, I pick one of them, David has. I don't know how many stickers David has. Cool. Okay. Then I would say D, and I would use a lowercase because the uppercase looks too much like a 0 if you're writing it quickly. So D is equal to number of stickers for David. Okay. All right. Do you know how many stickers Matt has? I don't, but they tell me something about it. Matt has twice as many stickers as David does right now. Oh, well, if David has D stickers, because I know that now, and Matt has twice as many, Matt must have 2 times. So this is number of stickers for Matt. Okay, perfect. How many stickers must Matt give David? So again, Matt has more. Matt needs to take some away and give to David. So they each have 120 stickers. See what I'm saying? And they would be equal then, right? So that's there you go. That's what we need. Here's kind of a big hint. if they end up with 120 stickers each, I mean, right? How many total stickers are there? Maybe that would be a big clue, because I'll bet you can figure out how many total stickers there are if they each have 120. And you can say, but they didn't start with 120 each. I understand. But Mac took some of his and gave them to David, so now they do have 120 stickers each, right? So whoop-de-doo. It doesn't matter that they didn't, the total number of stickers didn't change. It's not like somebody's mom came in with a box of more stickers. That's not what happened. However many total stickers they had at the beginning, even though they shifted them around between people, that's how many stickers they had at the end. Okay. There's your nudge. Couple different ways you could go about solving from here. This is, I believe, the first key point. Make sure that you do that as you set these problems up. Let's see. I did number 9 already. It's on the video page. It says 3C and number 9. So you're welcome to check that video for that one. If you're stuck on it and you say, hey, I'm stuck on this piece, make sure when you communicate back to me, tell me what you've done and where you're stuck. You can include an image of it. You can include a short video if you prefer, but let me know where you're running into trouble. 12 and 13, the sum of the first two terms of geometric sequence is 100 times the first term. Okay, well, same type of thing. I know they kind of look different because it's like, oh, this one's a geometric sequence. No, 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 no. It's still something I don't know and something I do know. So if I was doing this one, I would say I have two terms of a geometric sequence. I would stop right there. Geometric sequence. What's the first term of geometric sequence? I don't know. Pick something, right? A. Perfect. What's the next term in a geometric sequence? Remember, geometric, we multiply by a common ratio. So you could say A times R. Done. Love it. Okay, let's see what else it says. It says the sum of the first two terms. Got it. Then it says is. Okay. Is referring to that equality, right? Is 100 times the first term. Well, remember, this was our first term. 100 times the first term. You will need to do a little tiny bit of work here. But what's great is I got a feeling you're going to get a common value on the left-hand side, a common value on the right-hand side. I got this feeling that those A's may not be long for this problem. You may not have A's after you do one fancy step. But I will leave that to you as you go forward. Again, read what it's saying. This is the tough part because I know you have internal reaction to algebra problems. The sum of three consecutive negative integers is negative 201. Identify any variables. This is up to you. Pick a variable. You can say my first term is X. Done. They're consecutive integers. Who cares about the negative if they're consecutive? The first is 1. The next is consecutive. Got to be 1 more. So you think about it. If I had negative 8, what's the next consecutive number? Negative 7. What's the next consecutive number? Negative 6. So you can see I'm adding 1 each time. So if you think about that, you can make a sequence where you just add 1. If you want another number, you just add another 1. And then you can write an equation from that. You can find the integers. Now, what you saw from a prior section, or at least what I intended for you to see, and I hope you did, is that you could have defined any term. So you could have said, okay, my middle term is X. So the one before it would be X minus 1. The one in front of it would be X plus 1. And the reason that's sometimes nice is when you find the sum of an odd number, the plus 1 and the minus 1 go away, and you end up with just 3x. Depends on what you want, right? And for somebody to say, oh, that's the great way to do it. It's a way to do it. I don't know. Maybe it's a great way. Looks very similar to something down here with 3 consecutive numbers. Totally your choice on how you choose to do these problems. All right. Hopefully you get the idea. You're picking it up more. You're like, okay, I see what he's doing. He's kind of doing the same thing every time. He knows something. He doesn't know something else. That's how he's going to approach it. You're absolutely right. So if I was if I was solving question 5, actually, let me go back and see if there's a different question in part A that's very, very similar. Sometimes there is. Yeah, I guess this one, but this one's $2 and $1, which is fine. I guess that's fine. Let me try this one. I'm gonna try number 8. I'm gonna tell you why I'm gonna try number 8, because it's one where people sometimes say, "Oh my gosh, I got a lot of work to do." And I want to show you that if you go through these problems and you kind of think about what you're doing, you may not have a ton of extra work to do. Let's see why. Okay, there's 67 coins. It's only dimes and nickels, right? That's it. That's it. So if I was going through this problem and I said 67 coins, I wonder if I had 67 coins and every one of them was a dime, well, then I would have $6.70, wouldn't I? Yeah. That's if everyone was a dime. If every one of them was a nickel, right, I'd have half as much. So I'd have $3.35. And no, I didn't actually multiply there. I cut the other number in half because I'm efficient that way. All right. Well, notice the amount of money in the box is somewhere between them, which means I've got some nickels and some dimes. So if I was going to do this problem, what I might choose to do is say, what if all of the coins were nickels? That's 335, right? So take the $4.20 and take away $3.35. And let me grab my calculator here. So 335 minus 420 at 85 cents. Okay, right? But wait a minute now, I've already used up 67 coins. Well, kind of, in a sense, you have. You could picture this, like if I was teaching this to students, I'd say, well, just pretend that every one of these, I draw 67. Actually, I probably wouldn't. I just tell them to draw 67. I'd say every one of those is worth 5 cents. 5 cents, 5 cents, 5 cents the whole time. That's what this says. 67 coins at 5 cents each gives me $3.35. So if I count all of those out, I have used up out of my $4.20, $3.35. I still have to get 85 more cents, but I have to use dimes. So what you tell yourself is, well, then this thing where I used 5 cents, I got to put another 5 cents in there because that makes it a dime. 5 and 5 makes 10, right? And I need to do that. I need to add enough fives until I get to 0.85. So I can take nickels, 0.05, and divide by 0.85. So 0.85 divided by 0.05. 0.85 divided by 0.05 gives me 17. And what am I counting when I add those together? That would be 17 dimes. There's 67 coins. That means there's 50 nickels. And I'm done with the problem. Okay. I know your teacher never showed you that way, but you could do it. Nothing wrong with it. Now, if you're saying, well, wait, my teacher showed me how to do it algebraically. Okay, fine. What I'll do is I'll very quickly show you algebraically. I'll say, I know there's a number of nickels and a number of dimes, and together that makes 67 coins. And then I'll say something weird, like each nickel is 5 cents per nickel, and each dime, make that 10 cents for each dime, and that gives me $4.20. And then maybe I'd come down here and I'd say, oh, shoot, that's really, really close. If only I could eliminate one of the variables. So I'd take this entire thing and multiply it by 5 cents. And what I'd have is 0.05n plus 0.05d is equal to $3.35. And then we subtract and the ends go away. And what's left is 0.05 times the number of dimes is equal to 0.85 when you do the subtraction. And then to get d by itself, you would divide. Your end result would be 0.85 divided by 0.05. And guess what you end up with? Not a shock. You get 17. Okay. What I want you to see is all the work that you did algebraically, you can think about, which is why this whole chapter is not called algebra. It's called algebraic thinking. I could say, shoot, if everything was worth a nickel, that'd be 335. And then the only thing that's different, the only thing missing is I might have some dimes, which means I need to toss another nickel onto those to be able to make them worth dimes. and we can figure out how many of those we have. So pretty quick, meant to be pretty quick. And that technique is the technique you can use if you're doing problems like number 5, right? Number 5, what would I do? I would say, well, wait a minute, number 5, ooh, gosh, that looks really intense. Maybe. Or maybe it's like a super, super fast problem because I'm not going to freak out about it, right? Think about this. You have tickets. Tickets are either $2 or $3. Well, why don't I just take all 812 of them and pretend they're all $2 tickets, right? Okay, if everybody here was a student, they'd pay $2, and that would give me 1624. So now, when I look at how much money came in, which was actually 1912, and I take away the 1624, right? And so I'd say, oh, well, I had 1912. When I subtract, that gives me $288. But everybody who was not a student paid $1 more. So what I do is I'd have them, everybody's lined up and you're all students, but I have 288 more dollars. I've got to go kind of say, okay, I need 288 more dollars, and that's $1 from each of you. So the first 288 people come in. That means there are 288 non-students. I know, done. And you want the other one? Do you want the students? Fine. Take 812 total tickets, take away 288, and that will give you what you're looking for, which is 524. And you're done. You're done with this problem. I know, like to me, this is like, holy crap, math could be so cool. And for what you get to do, this is the joy of the age level that you're choosing, is if you go K through, honestly, 7th or even 8th grade, you are not going to see the algebra brought up quite the same way. If you're teaching late middle school all the way through high school, they are required to teach with algebra, not algebraic thinking. And that's probably why you never were taught this, because what you remember most is probably those high school years. And they would have focused on the actual algebra, where they say, how many tickets were there? Got it. Let S be the number of students. Let N be the number of non-students, right? And then they'd say S plus N is 812. And then you say, well, $2 per student plus $3 per non-student equals 1912. And they're trying to get you to use algebra to solve the problem. And hopefully what you saw today turns out, yeah, you don't actually need that. It might be helpful, but you don't need it. All right. That is it for now. Hopefully that's helpful for you. Off you go.